Okay, so it's the what is L of mu and sigma? It's the product of the Gaussians for each one of the individual events, independent, but each one draw from Gaussians with parameters that we try to estimate. So what's the probability that something happens? Just like in the previous example, it's a product of the individual probability of each one of the events, and we assume that the probability is given by this Gaussian. Now, writing this product, first let's get rid of the 1 over sigma times 1 over sigma times 1 over sigma, that sigma to the minus n, 1 over sigma to the n. Now, what happened to the exponent times exponent times exponent? Let's use this formula. E of x plus y is e of x times e of y. So if I have products of e to the power something, I'll write it as the summation of the individual parameters, and just make one big e over here to the exponent of the sum. So it's exponent of the sum of all these individual terms, which is 1 over 2 sigma squared times this summation. Xi, what we draw, minus mu that we are trying to estimate. And now we need a few algebraic tricks. Let's write x hat to x bar to be the sampled mean. That is, let's take the average of the sample. Why? I want the real average. I don't want to the errors that could be. I want to know what is the average of the whole population, not only of the subsets that I picked. Well, it's nice that you want it, but all you have are the sampled that you picked, the 30 people that you picked to measure the height. So let's use what we have. Let's x bar be the average of the xi's. And now S requires a bit algebraic stretching. S we would like to think about it as the variance, standard deviation of the of this expression. What we are showing is once x bar is defined, then s squared, that's how we define s squared. And now there is in the next slide the following result. The sigma of these terms that we see right here equals, just algebraic, no understanding, n times s squared plus n times x bar, the sampled mean, minus the actual mean mu. Okay, sampled mean is something that we can calculate. The real mean is something that we try to estimate, and so go for sigma. So I can write it in the following way. Minus sigma squared times the exponent of the first terms, minus n squared divided by 2 sigma squared, times, using this formula once again, the exponent of something of the individual, of n times x minus mu squared over 2 sigma squared. And we need to prove that this term, actually with this definition of x and s, that this term actually equals to this one, and that happens in the next slide. Where we write that sigma of x minus mu equals to exactly what we wanted. There is not too much understanding happening here. It's most, let's introduce more variables and subtract them immediately and just rearrange things. So let's just define this slide as boring arithmetic and moving it along. that was the final expression that we got, where here you noticed there is no more individual xi's. There is only the sum of the xi's, which is x bar, the average of the xi's, which is x bar, and the standard deviation that we guessed from the experiment, si's, that is depending on x bar and the data, and the two real value, mu that I don't know, and sigma square that I don't know. So how now I want to maximize this term. Not terribly difficult, but once again, I'll prefer to maximize the log of this expression. Log of this expression is log of this term plus log of this term plus log of this term, and log of y plus, because log of product is summation of the individual logs, log of this term using this formula. Once again, log of this term is minus n log sigma. Log of this term is, what is log of exponent? Log of exponent of x is just x. So from all this monster, we are left with just minus n over s squared divided by 2 sigma squared, and log of this part is just what you see over here. The minus is just the minus. Again, the exponents vanished because it's log of the exponent. And now it's very easy to take the derivative of this one, but now I do need to use a special partial derivative, special d, because I have two parameters, mu and sigma. Let's take the derivative of this expression by mu and ask it to be 0. The same goes for the derivative of sigma. White takes the 3 derivatives by sigma, takes the 3 derivatives by mu, and you'll get the answer that your best guess of mu, that is the one that will make this expression, which mu will make this expression equal 0. Answer, take mu to be 1 over n sigma of xi's. What is this? This is just x bar, what we estimated as the average out of the experiment. So it was a hard work to prove that our guess about the average is nothing but the average that maximizes the likelihood, so it has the highest chance to be the correct one. What about the variance, sigma square? Take the average of xi minus what you just estimated as the average. So that's just the average of the xi square, which is just the variance as we wanted it to be. Why is this a big deal? Because we had a great chance to, if we look at this expression, notice that if I calculated x wrongly, I have a good chance to also have mistakes in the calculation of sigma. Well, note, take mu as your average from the experiment, and that will lead itself that the maximum likelihood sigma is just what you'll guess as sigma, which is what? It's just the average. Let's write it down. Let's understand it exactly. It's just the average squares of distances from the estimated average. Okay, it's exactly what you wanted sigma to be. You are summing up the square of distances from the average to each individual parameters, summing them up, and take the average of these numbers. That's what you want, which will mean that square root of it is just the standard deviation. Great. So we have now ways to estimate both of them, again under the assumption that it's nothing but a Gaussian. Break.